Hi, welcome to this lecture on environmental adaptation of animals. Now on the second video on the oxygen and carbon dioxide, we will focus more detail on the diffusion of gases. So far we have learned that we have ideal gas law describing that what happens if we are changing the temperature or the volume, what happens for the pressure. And then we had the partial pressure that we can then understand that if we have in the air we have 20% of oxygen, then the pressure of oxygen in the atmosphere is 20% of the total pressure of the air. And then we have this Henry's law describing that what is the solubility of oxygen in the aquatic solutions. And we have learned that on the oxygen it was very low, in the carbon dioxide it was quite high. But let's go on the more detail. The principle in the diffusion of gases is the same, of course, as in the old solutes. So in the textbooks we have learned that if we have high salt concentration on one side, low salt concentration on the other side, then there is a diffusion of salt because there is a concentration gradient. But now we have to expand it from the concentration to chemical potential. So it goes toward the low chemical potential. And in the gases, we had to calculate the partial pressure. Because the partial pressure is now the good point. It works as well as in gas or in the solutions, or when you have on one side gas and on other side water. So it works on all cases. And that's why in the chills you can uptake oxygen from the environment if the water has more or higher partial pressure of oxygen than in the blood. And the tricky part in the gases was that because it's partial pressure, so it's not always going to low concentration. And sometimes it goes. So if you are aquatic animal, you have chills. If there is no temperature gradient, so your body temperature is the same as in the environment, and if the concentration gradient is minimal, so your body has as much salt as in the environment. In that case, the only thing that affects is the concentration. And that's why the oxygen is going from high concentration to low concentration. But otherwise, it's not the general rule. So it's general rule. So it might be that for example, in our lungs, we have air in one phase, and then from the air to the circulation, to the aquatic solution. Or we can have different salinity, like the fish in the marine or fish in the freshwater, etc. And let's go back on this diving beetle. So I postulated in the previous video that this air bubble it carries is a lung. I must have some kind of explanation for it. Well, first of all, if we have a swallow water, the partial pressure of oxygen in the atmosphere is 0.2 atm, and it has also 0.2 atm in the water. Because it's in equilibrium, the partial pressure is the same. But because we have the Henry's law describing how much oxygen can be dissolved in the water, so that's why in the atmosphere there's maybe 8 or 9 millimole per liter of oxygen, but in the water there's only 0.3. And when this beetle is diving, it will take some air from the atmosphere, and it will consume the oxygen from it. And sooner or later, it has used 50% of the oxygen, so that's why there's from the 8, oxygen concentration has been decreased to 4 millimole per liter. And at the same time, because it's in gas phase, the partial pressure is decreased. It works like an ideal gas law. And this makes then that, okay, although in the bubble there is 10 times higher concentration of oxygen, the oxygen is going from the water to the bubble of this gas. And that's why it's all the time respiring oxygen, taking oxygen from the surrounding water. And that's why this beetle can die for ages. And that's why these gas-aquatic solution interfaces are pretty tricky. That, okay, now the oxygen is going to place where there's 10 times higher concentration. Okay, but they are not tricky only for them. They are tricky also for humans. So for scuba diving, you are packing the lungs with high pressure air, because when you are diving deep, then the pressure in the water is quite high. It might be TATM, so it's 3 times higher already in 20 meters than in the surface. So that's why you pack the lungs with air to compensate it. And because when you have high concentration of air in the lungs, then the partial pressure of gases in the circulation will rise if you stay there for a long time. And it's been postulated that some of these can be forming microscopic gas bubbles, something that you can't see, but because they exist, it's then understandable that, okay, they can enlarge if the partial pressure is changing. So when we are coming on the surface to 1 atm pressure, these gas bubbles will enlarge because their pressure is now 1 atm, but on the surrounding water, the surrounding blood, there is 3 atm. So that means that, okay, the gas is going inside these bubbles, they will turn macroscopic and they will cause severe problems called decompression sickness. Okay, so these gas-aquatic interfaces are a little bit tricky, but on the other hand, they are as simple as the simple diffusion. So when we have chambers 2 and 1, and they have different partial pressure, then we have isolating layer with the distance x. If this layer is permeable for the gas, then this partial pressure difference is trying to reduce because there is a flux of gas. And this looks pretty much the same as in the beginning of this course we had the diffusion. So how many moles per second are moving, it depends on the graph, diffusion coefficient, then the partial pressure difference and the distance. Which means that, okay, if these chambers are far from each other, so you have thick isolating layer, the diffusion is slower. Or if you have, depending on what kind of gas you have, what is the temperature, what is the permeability for the gas in the isolating layer, then if you are affecting on that, then you can have faster or slower diffusion also. And this makes it pretty much in the same as in the diffusion that we had in the beginning of this course. We had the same material as in this figure already in the beginning of the course in a table. So there we had cell membrane, small cell, and different kind of structures with different kind of length. And then we were thinking, okay, how much time it will take before 50% of the concentration gradient is disappeared. And we can use it in the same way as how much time it will take before 50% of the partial pressure difference will be disappeared. And in the cell membrane or in the small cell, that's a biological scale. so much less than 1 second. But if you have 1 millimeter skeletal muscle, it will already take 1000 seconds. So that's a long time. And that's why already 100 years ago, August Krog was calculating that if you have a round cell with a radius larger than 1 millimeter, it can't work because there's never oxygen available there in the center. And after that, it's been calculated several times, even with computers, and it's still the same. If you have structure that 1 millimeter, larger than 1 millimeter, it's not working with diffusion. And that's why only very small animals, like the larvae of bonyfish, can rely on the direct diffusion of oxygen from the surrounding. And even they are in a high risk when they are growing. If they are growing faster than developing the circulation, they are going on hypoxic because the diffusion is getting slower if they are growing. So that's why they need to have circulation, respiration, etc. Okay. We have diffusion coefficient for different gases or different particles. And one of the things that is affecting us is that they might have different coefficient in the water and air. In the diffusion coefficient for oxygen in the air is 200,000 times higher than in the water. So that's why if you have, for example, sand, when it's dry and porous, so there is quite high oxygen concentration underground on the surface layers. But if you get the sand wet, then the oxygen partial pressure will drop drastically. Over here you can see they have measured the partial pressure of oxygen in the sand where there are eggs of turtle. It stays there quite high during the first 50 days. After that, the sand gets wet, the partial pressure will decrease practically to 0 for 2 days. And this means that during the hatching, most of the eggs are already dead. So in the oxygen particle, the diffusion is much higher in the air versus in the water. And even in carbon dioxide, although we learned that you can have dissolve quite high amount of carbon dioxide in the solution, it's still 9,000 times higher in the air than in the aquatic solutions. Okay, let's go a little bit more detail still on the partial pressure before ending. So we have learned that only the free gas molecules are contributing the partial pressure. So when the oxygen is bonded to hemoglobin, it disappears. So this then means that if you have hemoglobin, you can carry more oxygen in the circulation. It's still fluxing from the gills to circulation because it's binded. It disappears. But in the Antarctic ice fish that we learned in the beginning of this course, they didn't have the hemoglobin. So that's why they can't carry so much oxygen in the circulation. And the same way, we have carbon dioxide. Although we are going in the detail in the circulation a little bit later, but it's actually reacting with water molecules, forming carbonic acid and carbonate ions. And they are also disappeared. So that's why the direction of gas flows, it depends only for the free gas molecules that are not non-bonded or unreacted. So that's why if you are processing it, metabolizing it, you can carry more oxygen by binding it to something else. Or you can carry more carbon dioxide in the circulation when you are metabolizing it. Okay, let's put it in the summary. So in the environment we have oxygen, then we might have some oxygen in the blood, might have some oxygen in the cell, as well as we might have some carbon dioxide in all of these cases. And if you are binding the oxygen in the blood, you will remain higher partial pressure of oxygen in the environment than in the blood. But because the cells are all the time using the oxygen, then there's still higher partial pressure of the oxygen in the blood than in the cell. And also for carbon dioxide. So when the cell is producing carbon dioxide, some of the carbon dioxide in the blood is metabolized. And that will cause that there is all the time more of the partial pressure of carbon dioxide in the cell is higher than in the blood. But then you must be sure that there's also partial pressure of the carbon dioxide in the blood is higher than in the environment. So in that cases, that you have this gradient all the way from the environment to the cell on both oxygen and the carbon dioxide. In that case, it works. Thank you.